So having defined enthalpies and come up with the two types of enthalpies, exothermic and endothermic processes, the next thing that we will look at is the idea of calculating enthalpies. And that is, I think, the most important part of this topic. There are three ways in which enthalpies can be determined. We can determine enthalpies from what we shall call Bode energies. We shall know what exactly that is all about. Then we shall also be able to calculate enthalpies from experimental data, or what some people refer to as empirical data. Then we shall also calculate enthalpies from the Hess law, whatever that means. At the end of the day, if we can do that, then our objective will have been achieved. It is very important that you are able to do all that. But allow me to start from the very onset that whatever enthalpy we are going to calculate, you must first look at the definition. The definitions of the enthalpies is very important. You should be able to define an enthalpy and then go on to calculate. So don't disregard the definition. Now, we start off the topic by looking at the calculation of enthalpies from Bode energy. Now, we know what a Bode is. A Bode is that which holds items together, all substances, all particles. Of course, we are in chemistry, we are not interested in people, we are not interested in cows, we are not interested in stones. So we are interested in atoms, molecules and all that. So whatever holds atoms, molecules together to form a chemical substance is what you call a chemical bond. Now, and of course, from our Form 2 work, we know that we have three types of bond. That is ionic bond, we have covalent bond, and we have metallic bond. We have all those types of bonds. Now, in this particular topic, I will not be interested in ionic bond, not at the moment. I will later talk about ionic bond, because when I talk about the covalent, or when I talk about Bode energy in this particular lesson, I am strictly limiting myself to covalent bond. When I get to ionic bond, I will talk about a type of bond I'll call lattice energy. Now, so the energy that is involved in ionic bond will be called lattice energy. Now, allow me to just mention for metallic bond, it shall be called the atomization or sublimation. So if I look at sodium in solid state and I'm converting it to sodium I'm breaking the bond between the sodium atoms, the metallic bond between the sodium atoms. So you can't say I'm changing it from the solid state to gaseous state. So I call it sublimation energy. The energy, but we shall at this particular syllabus is this at our level we shall not say much about this. Actually, we shall not say anything about that. But note that the bond, when you break a metallic bond, you call that the sublimation energy. When you break an ionic bond, you call that lattice energy. So that will be shared for a future lesson. But for this particular lesson, I'm interested in the covalent bond. So definition. What is a Bode energy? Bode energy is the energy one required to break a mole of covalent bond. Note that whatever I am defining, I have to talk about the quantitative aspect of the same. Very important. I have to break a mole of covalent bond. So which reminds me, when you talked about the latent heat of vaporization, I may not have defined, but you know what vaporization is? To convert from the liquid state to the gaseous. So if I'm asked to define the latent heat of vaporization, I would say it is the energy required to convert 1 mole of the substance from its liquid state to gaseous state at its boiling point. Note, I have talked of a mole. So the quantitative aspect is crucial. It's crucial to include the quantitative aspect. Again, when you in Form 2, it was correct to say that ionization energy is the energy required to remove an electron from an atom from the outermost energy level of an atom in gaseous state. From this topic henceforth, that definition becomes wrong, because you are defining an energy. You're defining an energy term. So you must specify the quantity, because the amount of energy produced or absorbed will depend on how much is involved. So from today henceforth, the ionization energy is going to be the amount of energy required to remove a mole of electrons. A mole of electron, double underline. So without that, the definition becomes wrong. To remove a mole of electron from the outermost energy level of atoms in gaseous state. That will become our definition from today henceforth. So if you don't include the quantitative aspect, your definition becomes wrong. Who wants to write a wrong definition? Who wants zeros? I don't think any one of us want that. So include now that whenever you see that's an energy that you're defining, include the quantitative aspect. Now I have of course said that it's the energy required, because broad breaking must be endothermic. I have two things joined together. I want to put them apart. I have to supply energy. Energy must be supplied for a board to be broken. So it is energy required. Now, if you some tricky students will now say the energy involved. Hey, that's bright, because you have not committed yourself. You've not committed yourself. If you are not sure whether the energy is going to be required or is going to be absorbed, you can say it is the energy involved in breaking a mole of covariant bond. I just have to give you the benefit of doubt. But why go into all that? You know that to break a bond, energy must be supplied. Now, so chemical reactions shall be involved, there shall be two processes that accompany any chemical reaction. Now, we have to break bonds first, and bonds must be formed. We have come across that somewhere. Now, we said in Form 3 that nitrogen is rather unreactive. Though it is not a noble gas, it does not react. It's very inert. No wonder it is used to store semen, it is used to fill light bulb. Why? Because of its inert character. How did you explain that? We said that nitrogen has a nitrogen to nitrogen triple bond that requires a lot of energy to break. Now, therefore, we said that before the nitrogen reacts, you have to break the nitrogen to nitrogen triple bond. So that is exactly what happens in all reactions. Before two things react, you have to break the bonds. No wonder even substances that are very reactive, like hydrogen and oxygen, they react explosively. But if you mix hydrogen and oxygen, you can wait forever. Yes, keep waiting, continue waiting, you will really wait. They are not going to react until you introduce a burning split, and now an explosion will occur, what we call a pop sound. Yes, so you have to first supply a bit of energy that will be required to break the bond. Then after that, the reaction will continue. So there are two processes involved in a reaction. One will involve bond breaking, and I've just said that bond breaking is a endothermic process. Energy will have to be supplied. The other thing that will happen is that bonds will be formed. So
This balloon contains a mixture of hydrogen and oxygen. Ignite it and the hydrogen and oxygen combine, giving out energy and forming water. The individual atoms in each molecule are held together by chemical bonds. Hydrogen atoms are held together by a single bond. Oxygen atoms are held together by a double bond. When a reaction happens, these bonds are broken and new ones are made. Bond breaking requires energy. But when water molecules form, new bonds are made. Bond making gives out energy.
The enthalpy of a reaction will depend on which one is bigger. So if I draw an energy level diagram, now maybe these are where the reactants are, then I supply some energy, get to that much. Then when I get there, the reaction will start taking place, and I will get a certain amount of energy when the bonds are formed. So this is a difference. So this will be an exothermic process. Why? Because I'm getting more than I used. Now, other times you may supply that much, but you get that little. So this is going to be an endothermic process. Why? Because I'm getting less than I use. So we can also, even from both energies, we are going to have some exothermic and some endothermic processes. So now, having said that, let us, by means of an example, calculate the enthalpy of reaction given both energies. Example number 1.
Hydrogen and oxygen combine, giving out energy and forming water. The individual atoms in each molecule are held together by chemical bonds.
Identify the bonds that are broken. Look at the animation and identify the bonds that have been broken. So we can see hydrogen to hydrogen bonds, and 2 of them for that matter. Then we are breaking an oxygen to oxygen double bond. No, that is different from breaking 2 oxygen to oxygen single bonds. And what bonds are we forming? And there you are. You can, how many bonds can you count, and what bonds are those? I can see some oxygen to hydrogen bonds, and let's count. There are 4 of them.
Calculate the energy change for this reaction. We've got 2 molecules of hydrogen reacting with 1 molecule of oxygen to make 2 molecules of water. I'm showing you the structures of these molecules and the bond energies here, so pause the video and calculate the energy change for this reaction. Okay, so you can see that on the left-hand side we've got to break these bonds. And on the right-hand side we're going to make these bonds. The energy needed to break the bond between 2 hydrogen atoms is 436 kilojoules per mole. However, we've got 2 molecules of hydrogen, so we've got 2 of these bonds. We need to put in 872 kilojoules. Remember that the positive sign shows us that we're putting energy in to break these bonds. The energy required to break the oxygen double bond is 495 kilojoules per mole, and again the plus sign shows that we're putting energy in. Adding these values together gives us a total energy input of plus 1,367 kilojoules. The bond energy for an oxygen to hydrogen bond is 463 kilojoules per mole. We need to make this negative because we're making this bond, and making bonds is exothermic. Each water molecule has 2 of these bonds, and we've got 2 molecules of water. So we've got 4 of these bonds in total. Multiplying minus 463 by 4 gives us a total energy value of minus 1,852 kilojoules. To calculate the overall energy change, we subtract 1,852 kilojoules from 1,367 kilojoules, giving us a total of minus 485 kilojoules for the reaction.
There we are. you can have a look at that. What are we required to do? We are required to calculate the enthalpy of this reaction. This is what we call the substitution reaction. A substitution reaction, we are replacing a hydrogen with a chlorine in the presence of sunlight. We did that in organic one. Now we are given all these bond energies. How shall we go about this? This is the way to go about it. The first thing will be, and now we'll just sort of draw a trial balance. Is that what we used to call it? A balance sheet? Well, doesn't really matter so much. Now I want to identify the bonds that have been broken. And then I also want to know the bonds that have been formed. Bonds that have been broken and the bonds that have been formed. Now, in which case I may need to get the draw the structures of these molecules. So how does this look like? That is the methane. That's the way methane look like. This is the chlorine molecule. This is the chloromethane. I have 3 hydrogens and a chlorine. Now let me write the chlorine there, not because it has to be written there. Plus hydrogen chloride. Hydrogen chloride. That is it. That is what I have. That is structure. So all the bonds on this side must be broken. All the bonds on the other side will be formed. So what bonds am I breaking? And you just need to be systematic. I'm breaking a carbon to hydrogen bond. Right, hydrogen to carbon bond. How many carbon to hydrogen bonds am I breaking? 1, 2, 3, and 4. So 4 carbon to hydrogen bond. Now I'm told the carbon to hydrogen bond is 413 kilojoules per mole. So each of these bond is 413 kilojoules. So that is 413 multiplied by 4. Those are the number of bonds I'm breaking. I'm getting 1652 kilojoules for the 4. Now what other bond am I breaking? Now this is not broken down completely. I have atoms of carbon and hydrogen. Now I want to break the chlorine to chlorine bond. There's only one of them. I have one molecule. So that amounts to 219, of course, 239. I'm not multiplying by anything. So that gives me a total of, I hope it is 1891, 1800. I can write a positive there. I don't want to go to that direction. What bonds am I forming? Now, I'm forming a carbon to hydrogen bond. How many of them? 1, 2, 3. That is equal to 3 times, again, 413, which is equal to 1239 kilojoules for the 4 of them. What else am I forming? I have a carbon to hydrogen bond there, only one of them. Carbon to hydrogen, carbon to chlorine, sorry. That is 339. And then I have a hydrogen to chlorine bond there, that is 427. So that amounts to 2005 kilojoules. So that is the amount of energy that I get. And I would want us to visualize now what is the enthalpy of that reaction. Now let's draw a small energy level diagram here. So I'm starting from here with this reactants supplying how much energy? 1891, and then getting 2005 to get the product. This is the enthalpy. How much is that? We just need to subtract, and is it positive or negative? You see, I'm getting more than I used. So when I subtract the 2, I think it is giving me 144 kilojoules. is it negative or positive? That is the question. Is it negative? So note that this is negative and this is positive. I cannot, so the negative is more than the positive, so that gives me a negative enthalpy change, negative 144 kilojoules. Now, do I add per mole? Yes, I can add per mole because it's per mole of methane. It is per mole of chlorine, per mole of, I have one as written there. So I may be asked now to write the thermochemical equation. How will the thermochemical equation look like? All I need is the balanced chemical reaction. Then I write delta H is equal to negative 144 small k capital J properly written. That will give me the thermochemical equation. This is energy level diagram, but it's wrong. Why is it wrong? I have no treble. One, I have no treble. This is energy, and this is the reaction progress. I have not written the balance equation, so that is very wrong. So I have to write the chemical substances that are involved. The CH4 plus chlorine, the CH3Cl plus HCl. That is a proper energy level diagram. Draw the axis and draw both reaction progress. Reaction progress, energy in kilojoules. Now, where am I starting from? I'm starting with methane plus chlorine. Supply some energy, get some energy. Not, so what am I getting? CH3Cl plus hydrogen chloride in gaseous state. In a gaseous state, then I drew an arrow in that direction, 144 kilojoules. I don't have to write a negative. It is obviously negative because of the direction of that arrow. That is it, the energy level diagram for that particular process. I've also talked about the thermochemical equation, CH4 plus Cl2. The states are important in thermochemical equation. It depends. The amount of energy you get depends on the state. So delta H is equal to negative 144 kilojoules. I add per mole, doesn't make it wrong. Because per mole of that, per mole of that, per mole of that, that is a thermochemical equation, that is the energy level diagram. Are we ready for the second example? That is our second example. What is the enthalpy of a reaction of the following? I think that's the enthalpy of combustion of methanol. Yeah, the combustion of methanol. We are given that, and then we are given those board energies. We want to work out the enthalpy of that reaction. So what do? Let us get the boards broken and the boards formed. So before we get to that, let's draw up this. Okay, that is the structure of methanol. The oxygen from our form 2 work is an oxygen double bond forming carbon 4 dioxide. That's the way we drew carbon 4 dioxide and H2O. We have 4 of that, we have 2 of that, 3 of that, we have 2 of that. Yeah, those are the structures of the substance involved. So what bonds are we breaking? All the bonds on this side are being broken, all the bonds on the other side are being formed. So bond breaking, now let me be systematic. I have a CH bond. But how many of the CH bonds do I have? 1, 2, 3. 3 CH for each molecule, but there are 2 molecules, therefore 6 CH. So that is 6 times the CH bond is 414. You can be working out the variance as I As I continue, no, I can work out for that's coming to 1992. Worked it out. Now let's get to the other bond that is being formed, that is being broken. Here we have a carbon to oxygen CGO bond. Carbon to oxygen CGO bond. Note that there are two carbon to oxygen bonds. There is a CGO bond here, there is a double bond. You are not breaking the double bond. We are breaking the CGO bond. So there is one per molecule, but there are two such molecules. So 2, that is 2 times the carbon, that is 360, and that gives me 720. I am sure of that. That is 720. Yeah, 720. Now where do I go after that? I've broken that and all this, then I break the OH bond. How many? 1 times 2. 2 OH bond. That is 2 times OH. Where are you, Mr. OH? Yes, 464. That gives me a total of what? A total of 928. 928. Yes, 928. I move on to the oxygen to oxygen bond, double bond. Oxygen to oxygen double bond from my form. But there are 3 of them. That is 3 times. Where is the oxygen? 498. 498, I said. 498, that is equal to 1992. 1992. So the total amount of energy there, just need to add that up to 6124. You can write a positive there. We know the energy is going to be required for that process. Then we cross over to the other side. So what do I have? A carbon to oxygen double bond. How many? 1, 2 times 2. Each carbon to carbon 4 oxygen has 2 carbon to oxygen double bond. But there are 2 carbon 4 oxygen. Let's 4 of them. So 4 times the oxygen double. Look, be careful. 799. It's a very strong bond. Very strong bond. That amount to that 196, 3,196. We can confirm that. And what other bond is being formed? Hydrogen to oxygen. Oxygen to hydrogen bond. 1, 2 times 2. That is 8. 8 times OH, 464. What does that amount to? That is 712. Hopefully, that's 712. So the total amount of energy that is produced is 6908, 6908, and that is of course negative. So looking at that reaction, is it exothermic or endothermic? You realize that the energy that is produced in bond formation is more than the energy that was required to break bond. So it's an exothermic process. We just need to subtract them, get 1282 kilojoules, small k, that's what makes the K lowercase and capital J. Now, is it negative or positive? Of course, negative. It's of course negative. The energy that is used in bond breaking is less than the energy that is produced during the bond formation. So it's an exothermic process. Now, can I add per mole here? Of course no. Of course no. Per mole of what? Per mole of what? Because for this, I burnt 2 mole of. To get this amount of energy, I burnt 2 mole of methanol in 3 moles of oxygen from 2 moles of. So I don't have per mole of anything. So if I'm asked to write the thermochemical equation, delta H is equal to negative 1282 kilojoules. It is not per. It's not per mole because it's for 2 moles of that. It's for that particular reaction. So when I burn 2 moles of methanol in 3 moles of oxygen, I get that amount of energy. Would you draw the energy level diagram? I've written the thermochemical equation for you. Can you please draw the energy level diagram? I'm not talking so that you can concentrate. Equations must be balanced. Very good for 0 mark, so I cannot interpret your diagram. So time or reaction progress, minutes, seconds, and energy in kilojoules, not per mole, just kilojoules. So this is the activation energy, that is energy. Energy. Now I want to warn us against a practice that is very common. The idea of trying to use the enthalpy of the delta H is equal to heat of product minus heat of reactant. So you want to assume that the product, the energy of the product we have calculated as 6908 minus the energy of the reactant as 6124. You want to put it that way. Do you know you don't know the heat of the product? You don't know the heat of the product. You don't have it. You don't have this value. This reading you don't have. You don't have it. What you have are these readings and that reading. You don't have this value and that value. If you had this value and that value, you could have used that expression. So this one, please avoid it. It will always give you the wrong. Why is it giving you wrong values? Because you don't know the energy of a reactant. You don't know the total energy content of the reactant. What you know is the energy that has been supplied. The energy that has been supplied to that. Energy that has been released. Not the energy that it contained. Not the energy that it now contains. You don't have it. So avoid that as much as possible. Avoid it. It will not give you the correct value. So this should not be used because you don't know the heat of the product, you don't know the heat of the reactant. Just draw an energy level there, or just add them up. Inspect them, look at which one is bigger, which one is smaller, and then from the relationship, then you can just subtract normally and put the side depending on the relative quantities of the two. Now, are we ready for another example? Now, this one you will do for yourself. Do this one for yourself, my friend. I hope you are ready. The answer should be 296 kilojoules per mole. You can proceed to draw an energy level diagram, write a thermochemical equation for that, and if you can do that, then you are okay.
Here's one final example for you to try. This shows the complete combustion of methane and oxygen. Pause the video and work out the energy change. Okay, so on the left-hand side, we can see that we're going to break all of these bonds. And on the right-hand side, we're going to make these bonds. So first, we've got 4 carbon to hydrogen bonds in the methane molecule. The bond energy of a carbon to hydrogen bond is 413 kilojoules per mole. Multiplying this number by 4 gives us a value of 1,652. This needs to be positive, as breaking bonds is endothermic. We've also got to break the double bond in the oxygen molecule. The bond energy of this is 495 kilojoules per mole. However, as you can see, we've got 2 molecules of oxygen, so we've got to multiply this number by 2. This gives us 990, and remember that this also has to be positive. Adding together 1,652 and 990 gives us a total bond energy of plus 2,642. On the right-hand side, we're going to make these bonds in the carbon dioxide molecule. The energy of the carbon to oxygen bond is 799 kilojoules per mole. However, each molecule contains 2 carbon to oxygen bonds, so we need to multiply this by 2, giving us 1,598. We also need to make this negative as we're making these bonds. Okay, next we're going to make the oxygen to hydrogen bonds in water. The bond energy of an oxygen to hydrogen bond is 463 kilojoules per mole, and we've got 2 of these bonds in each molecule of water. However, we've got 2 water molecules, so we've got 4 of these bonds in total. Multiplying 463 by 4 gives us a total of 1,852. Remember, this has to be a negative number as we're making these bonds. Adding together minus 1,598 and minus 1,852 gives us a total of minus 3,450. To work out the total energy change for the reaction, we subtract 3,450 from 2,642. This gives us a value of minus 808 kilojoules, and that's our final answer, shown